Hi, my name is Noah Gift, and I'm the author of Practical MLOps. And today I'm going to talk about one of the chapters on AutoML. And in particular, AutoML is an exciting new technology because it allows you to do things that are really boring and error prone, like setting hyperparameters, and use platforms to automate that technology. I'm also going to talk about this concept that I call Kaizen ML, which is improving every single aspect of machine learning. If you think about some of the most important problems in the world, autonomous vehicles, cancer detection, drug discovery, vaccines, really what we care about is the outcome. We care less about exactly all the ins and outs of, what hyperparameter I set, but, am I getting a new model into production? And is it making things better? Is it making things the same? Or are they getting worse? And that's really the concept with Kaizen ML is every single part of the solution from the data to the features to the model to the deployment of the software to the business problem. It's all being looked at and automated in a comprehensive way so that the outcome is really what's important. So let's go ahead and take a look at some of these details in the book Practical MLOps, and we're ready to go. What I was going to start with is this repository, just to cover some of the concepts, specifics of computer vision now. And in particular, one of the things I'll bring up is this trends here, which I think is an important concept to be aware of. That one of the things that we're seeing in particular with computer vision is that there's an explosion of these hardware devices now. So this is called AWS Deep Lens, which is a prototyping tool for building computer vision solutions, Raspberry Pis, the Intel Movidius. But in general, computer vision has a very deep relationship with these prototyping devices, and we're seeing more and more of these. And I'm going to show you why that's the case. And in particular, one of the things that we're seeing is that for the last 40 years or so, this was a very exciting time in history. The CPUs were getting faster and faster and faster. And one of the things that happened was that then those speed changes started to diminish. And now, since right around 2015, the CPU is really not doing very well in terms of the clock speed improvements. So as a result, what's happening is that they need to find other ways to improve performance. And if you look at Amdahl's law in particular, what Amdahl's law says is that even if your code is reasonably parallel, there's diminishing returns. And even in the most parallel situation, look here, you only can get, let's say, a 20 times speed improvement, even with 1,000 cores. So with deep learning. So now we have this problem where the clock speed is not improving, and then also parallelization has some limits to it. And so one of the ways that the computer industry is handling this starts to go into these hardware devices like the ones I just talked about. And in particular, the TPU, I think, is one of the first chips that was designed specifically for working with deep learning. And it was in production since 2015, and Google uses it for search, translation, photos. And the important thing to be aware of is that this TPU itself is highly integrated with TensorFlow framework. And so this is one of the things that we'll see is that these technology companies are not only building new chips specifically for deep learning, but they're also building the framework that works with it. And then in the case of a company like Google, they're also they have access to things that other companies don't have access to because they have search data, translation data, photo data. So they really have a fully vertically integrated AI stack. And that's one of the advantages that they have in terms of what they're doing with AI and ML. And if we look at CPU, here's an example of how CPU technology works, is that it's really a general purpose technology. It isn't designed to be parallel. And so that's why with deep learning, many people have migrated to doing GPU based workloads because they're much more parallel. But the issue with GPUs is that even though they're highly parallel, they weren't designed for doing deep learning, right? They're a stopgap measure. And that's where something like a TPU comes into play. Is a TPU is specifically designed for deep learning, is specifically designed to work with TensorFlow framework, and it is much more dense and also more efficient. And so this is just one example of a chip that does this, but there's many different companies now that are doing something very similar for computer vision. And so really the end result here is that CPUs are stuck in 3% performance growth. And so the result is that there's going to be a lot of other hardware technologies that are at play here. Amazon has ARM technologies, NVIDIA's doing things. AMD has a lot of new GPU technologies. Intel, there's also FPGAs, which I think is an interesting example as well, where if you look at what's happening with FPGAs, that they're actually much more dense than a GPU, and they also work very well for many different kinds of instructions, where a GPU is really good at doing the same operation over and over again. But with a FPGA, you can do lots of different, let's say, training jobs or different instructions, and it has a much more density. So this could also be one of the solutions that people could use, is they could specifically program a FPGA with maybe a customized set of instructions for their deep learning task that they want to do, and even design a framework, maybe your own deep learning framework from scratch. So you could design the hardware and also the software all simultaneously, and then programmatically put that onto a cloud. So I think we're seeing much more advanced solutions for deep learning and computer vision. I'll get into this a little bit later, but also Apple has this A12 chip here that we see A11, A12, A13, A14, M1. They have a whole series that they're developing where they have actually the machine learning predictions built directly into the chip. And the result of this is that they also have a full vertically integrated AI ML stack, right? Because they own the mobile phone, they own the hardware, they own the software platform, the operating system. They also have the development tools with, which we'll see in a little bit, with Create ML. So there's a very complex interaction here that's very powerful that you get by again controlling every single aspect of the system. And we'll get into this. I'm going to show some demos later where we get and build a model. But in a nutshell, they have a very high level framework that allows them to take advantage of pre-existing computer vision models as well as train one yourself in a nutshell. And so I guess probably the last thing that I'll say here is that what you'll see now is that everybody that's doing something interesting is most likely using a platform, and they're most likely using hardware, right? So if you look at self-driving cars, if you look at mobile technology, that most likely they're using some kind of large-scale platform as well as custom hardware. And you see tons of different examples of this: SageMaker, Deep Lens, Google's AI platform, Azure has one as well. So it's just something to be aware of. Now that's maybe setting the stage a little bit here for the emerging hardware and AI. Let's talk briefly as well. Let me just also cover this. Let's go back to that repo here and go to the second lecture here. And just really briefly, I'll just mention that some things you may want to be aware of is that, and we talked about this I think before, but TensorFlow Playground is a great place to get intuition around deep learning. The other one is that this course here, there's a link to it, has some very good information about the basics of deep learning. But some of the other things that we're seeing in terms of computer vision, emerging technologies, generative modeling, we see this a lot where computers are building people, right? We see they're building, artificial faces, music, and also with TensorFlow technology, you can download pre-trained models and use those pre-trained models to later maybe convert it to a system where you're using transfer learning and you can tweak it. And in particular, I think there's one here that I'll show you that here's a good example of transfer learning in practice, is that with transfer learning, one of the neat things you can do is you can take a shortcut and you can use a fully trained convolutional neural network to download it, and you can just chop off the last layer and then replace it with your own. So here's a good example where in the case of maybe the Google cloud platform or maybe a pre-trained model, you can take one that was trained on very expensive hardware that maybe was trained also on a very large data set that you would never have access to. It's just only available to researchers. Once you've done all that, you could download their model, let's say from the TensorFlow hub, and then just change the very last part of the model, and then it will work pretty well on the problem that you're trying to solve. So how would it work? You can see here, you could go to Keras, and you could just say, hey, I want this model right here, and I want to change this last layer. And notice it says pre-trainable false. It freezes the weights. You just say flatten, and then you've got basically 75% accuracy. And then you could slightly tweak it a little bit and train it with some new data. So this, I think, is also a very interesting new emerging technique, is, again, to go to somewhere like this. We'll go to, TF Hub here and go to this image, download it, find some model here that looks like it's good, and then use transfer learning, tweak it, maybe train it a little bit on your model. So there's a few things here that I think are interesting in terms of emerging technologies to be aware of. The other thing that I'll mention that we briefly talked about was this OpenAI Gym concept, and again, the idea here is that you have an agent. The agent takes action on the environment, and then you have a reward, and basically you don't really know what's going to happen until you do experimentation. But one of the frameworks here that's pretty good to play around with is this OpenAI Gym, and you can see this is kind of a conceptual idea where you could create some actions again that you want to reward, maybe eat a pellet, go towards a ghost, go to an empty space. You don't know until you experiment with it, and then you observe what happens. Now you can see here, I think we have an example here somewhere where I have it running. But anyway, the core concept here is that it's a feedback loop, and you have to try experiments. Let's now kind of shift gears here for something which I think is a very important concept that ties into this, is how do we use higher level tools to take advantage of building computer vision models quickly so we don't spend a lot of time working on things that are inefficient. And this is where AutoML technology is very powerful. And we're going to go through and use this today to build some computer vision models that take a second or 2 seconds, and we can train the computer vision model and immediately start using it. So in a nutshell, though, let's start with the AutoML concepts here. Let's just kind of scroll down here. And I think one of the things to be aware of, I think that's a good analogy for AutoML, is to think about food. And in particular with food, you could think of food and machine learning. They're very similar. And if you think about food, there's lots of different ways to do the same thing. So one of the things that's easy to do is if you're in school and you're studying for a final exam and you're very busy, and you don't want to waste time going to the restaurant, you just open up your mobile phone, you click a button, and then the pizza comes or some food delivery comes, right? It's still food. Just because you didn't make it doesn't mean it's not food. You may not have as much control over it though because someone else gave it to you. So I would say this is a lot like an API, right? Where you're calling out to an API and it does exactly what you want it to do. Maybe it does computer vision, object detection, or natural language processing. But that's just one example. Similarly, let's say again, you're studying for an exam and you're busy. You may not want to cook all the food yourself. Instead, you go to your refrigerator, you grab a frozen pizza, you put it into the oven, and then you still have a pizza, right? It's very similar to the pizza delivery, except for you just put it in the oven. I would say AutoML is kind of similar, where in many cases, you can just take the data, put it into a machine, click a button, and then it trains a model. But then this doesn't mean it's the only thing you can do. You also, if you wanted to, you could go into your kitchen and you could grab the flour, you could grab the yeast, you could grab some salt, maybe a little bit of sugar, making some dough, let it rise for several hours, punch the dough down, roll the dough out, make a pizza dough. You could take hours and hours and hours, but you could make your own pizza as well. A lot of times that's what it's like to train a model from scratch. Now, there's some advantages to making your own pizza dough because you can decide all the ingredients that you want, maybe use very fresh ingredients, and you are very careful, but it's also very labor intensive. So I think that's something to be aware of, is that there are many different ways to eat food, and there's many different ways to build models with machine learning. And it doesn't mean that one is necessarily better than the other. It really depends on the context that you're in and what your organization is trying to do. I think it's similar. I would call that when people are not aware of this is something I would call magical thinking, right? Like, again, if you go back here, if someone says, well, pizza delivery, that's not pizza. Well, no, it is. It is pizza. You may not accept the fact that it's still food because you didn't make it, but it is. Similarly, if you ask a very small kid, maybe they only want you to get pizza delivery because they want the pizza from the pizza company. But if you make the food themselves, sometimes they get very upset. Oh, you can't make pizza. Only Domino's makes pizza, right? Like this is magical thinking. The same goes with COVID is another one. People say, oh, it's just the flu. It's just the same thing. No, it's a very different thing. COVID is a very different fatality rate, infection fatality rate than the flu. They're not the same thing. So this is another form of magical thinking. Similarly, if you think about AutoML, I think many people are afraid that because the automation occurs that, it's going to automate their job or, and they don't want to do it. But that's also magical thinking, that there's lots of different examples of people not accepting reality. And the best way to accept reality is to, on a case-by-case basis, look at it. And one of the things that you can do is use this MLOps philosophy. And so I think a very good example of this was, if you've ever read this book called Codebreaker, a very good book. It talks about how there's two companies that in the United States that helped create the mRNA vaccine. There was Pfizer and Moderna. Jennifer Doudna was one of the people that helped create the vaccine for Pfizer. And then Dr. Zhang was the person that helped with Moderna. And in both cases, they really quickly took their research and they put it into production using automation, right? So they were able to automate the CRISPR technology and put it into production. So I think there's a big takeaway if we look at the data science and machine learning, that too many people were only focused on research, and more people need to be like these two people, which is, hey, let's focus on getting the results so we can save the world or solve a problem. And in particular, I think what we see from the COVID vaccine example is if you have a sense of urgency, you can very quickly solve problems, right? You can take the research and get right into production and operationalizing things. And I think a good example of this, if we kind of scroll down a little bit, is this systems methodology is really what I would use, is that from a high level, when you think about computer vision, you think about machine learning, that it isn't necessarily what you hear people talk about on Kaggle, because data science is really like a behavior, right? It isn't necessarily the solution. Data science just means that you're applying critical thinking, you're looking at data. And AutoML also isn't necessarily a solution, it's just a technique. So they're not good or bad, they're just things to be aware of. The real solution is the systems methodology. And the systems methodology means that every single aspect of computer vision, machine learning needs to be automated. Maybe AutoML is one component, the data engineering pipeline. So for example, if the data for a self-driving car, let's say that you only once a year could get all the self-driving car data one time per year because it's so difficult, you have a year feedback loop that you have a problem and you don't know what happened in the last year. It could have been a lot of different changes. And so you now have to automate the collection of the data. Now, if you could, from self-driving cars, every single time the data has got new data from the cameras or the vehicle information, if it automatically goes somewhere, then you've solved a very important part of the system. Likewise, if you're able to automatically take the data and create different features and store those features in a form that makes it easy to do training, you're able to have a better system. Same with software. I think many companies have very bad software systems because they don't automatically test their software deployment. I've worked at many companies where they don't automatically deploy their software. So that's a weak hole. Also, if you're not using cloud computing, you could have real problems with scaling the training and also scaling the prediction. Likewise, there's newer techniques like data drift, where you're able to detect changes in the data from the last time you train the model and automatically do it. So really, this is a very small amount of what's happening. This is a very small amount of what's happening in a real world system. All of these things go together and they create MLOps, which allows you to put a model into production, and not only just put it into production, but to continuously maintain the system so that there's a feedback loop and you're actually continuously improving things. So I think this is one of the most important things to be aware of in the real world, is that there's a holistic approach where everything is constantly being improved and automated. And that's how the real world works with machine learning and AI. And you can see examples of this in history. In particular, there was Industrial Revolution, which was 1760 to 1840, where you had steam automation and coal machines. 1870 was another one where you had electrical systems being automated. In general, automation is something that is always going to occur. And if humans are doing a lot of things, eventually the humans won't be doing those things and machines will be doing things. And a really good example of this is there's a show, if you have Disney Plus, you can see example of it, called Made in a Day. And they show you all of the different automation systems, from Teslas, how the Teslas are made, guitars, Tabasco, rockets. And in particular, you'll see that everything is using machines to build things more quickly. So why would it be that machine learning and AI would be any different? Of course, we're going to use machines and everything's going to be automated. Humans still have to orchestrate what's happening and control it. But I think that's what we're really going to see, is that things that are happening now, like special configurations or people in Kaggle tweaking the hyperparameters, it's not even possible that that's going to be the future. You're going to use full automation systems and platforms. Like one of the examples I give here is imagine you go to Tesla and you tell the people at Tesla, we're not going to build cars automatically anymore because you're not doing it right. I'm going to come in here with my wrench and I'm going to build. Someone would laugh at you because it's not possible to get the scale. Same with machine learning and AI is people need to focus on the outcome, right? Which is, are we building models that do accurate predictions? Is it improving the business outcomes of the company? These are all things to be aware of. So example here would be data science 1.0 is what we see a lot of is people are tweaking things, they're on Kaggle, they're saying, look at this, I did this and this, but they're manually doing things. It's like putting a Tesla together with a wrench. But in the future, and we're already starting to see this, is that in fact, many machine learning problems, you don't even need to write any code. Instead, you use higher level systems like AutoML systems, platform systems. And I think this is really actually already happening, and you'll see this in a second. Now, one of the other things to be aware of too is that I think AutoML is one of those technologies that people are really afraid of, but it would be like saying that the semi-autonomous vehicle is something to be afraid of, when all it does is help the human have more time in rush hour, right? If you've ever been in a car like a Tesla or a Mercedes, where you can turn on the active cruise control and they just will go and follow the car in front of you, but you still have to be on the wheel. It's similar with AutoML, is it's a very, very small part of it. And so you can see here that what I think is going to occur is that we're going to have this MLOps industrial revolution, and automation is really this key driver, and that data is going to be the thing that is going to be valuable, because data is something that really is not reproducible. You can't create data. You can only basically, if you have the data, then you have the competitive advantage. But what we will see is that these automation tools, that they're going to drive the price down, where basically everybody's going to have some kind of automation. The humans, it doesn't make sense that humans are going to be doing hyperparameter tuning and doing all of these different things. Instead, we're going to use automation tools. And a really good example would be if you look at the Linux operating system. I remember when you used to pay for operating systems, like there was Solaris, AIX, HPUX, all these mainframes, but Linux was actually not as good as those other technologies, but it was free. And so even if the AutoML isn't as good as the human, eventually it's so cheap to do AutoML that eventually it'll get to zero. And so what I think we're seeing already is that data scientists, the price is going to go down, right? Because that's maybe not even a job anymore. But what we will see is machine learning engineering going up, because people want to put things into production, and they'll use technologies like AutoML that do all the work for you. And so really the outcome will be more important than the research. Now, if we scroll here down and we think about what Kaizen ML is versus AutoML, is that Kaizen is the concept of automatically improving process, which we've seen throughout history. This is how automation works: is you always make things better, improve it. AutoML, all it does is automatically create the model creation. So really, they're kind of two separate things. AutoML is a very, very tiny part of the entire system that's getting automated. So when you hear AutoML, I think it's important to be aware that it does not replace data science. The Kaizen ML, or automation of the entire system, is what's actually one of the biggest changes that's occurring. And so let's look at some of the things that are inside of that. And one of them is this feature store concept. And in particular, let's take a look at this in a larger picture here, is that here's what's happening in the first version of data science that many people are aware of, that you would have manually, everybody would be pulling the data in, changing fields, dropping columns, manipulating things. And we know that this was a real problem because it's manual. Just like building a Tesla with a wrench is manual, right? It doesn't even make sense. Why would you do that? You need to be fully automated. And this is where the data ops takes place, right? Where you're saying, I want automated transformation, automatic cleaning, and validation. And what happens is that this creates a feature store. And once you're able to clean the data and build it so that it's high quality features, now you're able to automate every single part of the machine learning pipeline. You can continuously deploy the model into production. So imagine again a Tesla, they deploy constantly new updates to the vehicle. In order to do that, you must have high quality automation before that, because you don't want to be putting bad machine learning models into the vehicles. But also you need the capability to automatically deploy it to the vehicle. So that's where the continuous delivery comes in. AutoML as well, again, is only a very small component of this, but it's why would you manually do something when every other part of your system is fully automated? Likewise with training and also prediction, where you need the cloud to be able to elastically expand and contract automatically. So really, Kaizen ML is every single thing is automated in addition to the model tuning and the hyperparameter tuning. So really AutoML is not a replacement of, let's say, what data scientist does. This is more of an enhancement, Kaizen ML, of what's happening with data science. So let's take a look at this feature store in particular. And so one of the things to be aware of is that it's a location for storing data so that you can more quickly build things. And in particular, if we look at this picture here, I think this is maybe the main takeaway, is that next time someone tells you that AutoML, it won't work, or they have a complaint about it, or they say it's what data science does, just be aware that this is very tiny part of the real world problem. Again, imagine a company like Tesla that's building autonomous vehicles, that I'm sure they have this. I don't know for a fact, but I'm sure they have some form of automated ML. But how does that give the model to the car, right? That's a totally separate process. You need to have automatic testing of your software. You need to have automatic deployment. You need to have elasticity where the model is being trained. So really the whole thing is what gets the model into production. And AutoML is just one component of what's happening. Let's take a look at also this feature store, which I think is a very important one to be aware of, is that Uber has a good example of this feature store technology. They've used it, I think, since at least 2016, maybe. They've had this, and you can see that one of the things that they do is that the motivation was they wanted to get faster at building models, putting it into production, and they really needed to make things quicker, right? And that's what they want to do, a short time frame. And that's what we're seeing a lot with machine learning and AI. And in particular, let me just scroll down here to look at the workflow. They designed the system to manage the data, which is what we were just talking about, train the model, evaluate the model, deploy the model, make the predictions, and monitor the predictions. So this feedback loop in the real world is what any large company is going to need to do, is have scalability, reliability, reproducibility, ease of use, and automation. And so a human by themselves really can't do this without using a platform like, for example, this Michelangelo platform or some other platform. And likewise, if you take a look at this, this feature store concept, is that you're basically having this automation build all the features so that later your system can go through and build out quickly new machine learning models. So let me show you another example, which would be this example. This is Databricks, which is another more of like a a commercial feature store platform, you have the raw data, you have all of this featureization. So maybe you have different data sets that are getting combined, they're being transformed, maybe they're being aggregated, and then you register and you create metadata that says, here's all my features available. So this would be a lot like a big walk-in freezer at a restaurant where you have all the different meat and the vegetables and the flour and the oil. All this is stored inside of the walk-in freezer. So then later you can make lots of different meals. So then if you notice here that the training now can use the feature provider, you can do batch-based training, which you maybe train once a day. You can do online, so every time new data gets updated, you can do new incremental predictions, and you can serve out the data as well as have clients like the end users get access to this data. So really, in a nutshell, this is yet one more aspect of fully automating machine learning into production. So let's take a look at the difference between a feature store and a data warehouse. I think the biggest thing to be aware of is that with a data warehouse, many people are aware of how those work. They're essentially a high quality business intelligence input. You can do reporting, you can do dashboards, you can do business intelligence. And really the concept is you're taking the data maybe from multiple databases or different locations and creating them so that they're ready to be used, so that you can figure out who are your most valuable customers, what's our profit and loss, those kind of business intelligence solutions. And the inputs could be streaming data, could be batch data, but with a feature store, it's kind of similar, except for instead of you serving out reports that are basically descriptive statistics, you're doing predictions. And so the feature store is what you would use to do training, to train models, unsupervised machine learning models, supervised machine learning models, also to do predictions, and also the clients themselves would get access to the reusable quality machine learning inputs. So really it has a lot of similarity, except for the users are not things like dashboards, they're machine learning systems. And now we can get into some of the hands-on work here and talk a little bit about Apple's ecosystem. And so, Apple in a way seems like a strange candidate to be around machine learning tools until you look into it a little bit deeper and realize that they have a really high profit and also gross revenue. They made 55 billion in apps in 2019, 72 billion in 2020. So the more they can allow people to create apps, the more money they make because they're the marketplace. And in particular, if we scroll down here, one of the reasons why is they have their own chips that are very, very powerful chips for doing predictions and also for doing training. And you can see this is the M1 chip here that's in the laptop I have right now. And it can do training and prediction. And part of it is that it works well with their Core ML library. And Core ML also can use Python code and convert a model from, let's say, TensorFlow to the Core ML framework. So basically, here's some of the things to be aware of. Apple's Create ML framework can be used to create AutoML. You can download a pre-trained model and convert it to Core ML. And one location is this TF Hub, which we already talked about. You can also train a model yourself for writing the code and convert it using a Python library called Core ML Tools. So there's several different ways that you can use this framework. So in a nutshell, if we take a look at it, it allows you to create Core ML models, preview the model performance, train the model on your Mac, and take advantage of this really powerful M1 chip. You can also pause, save, and resume your training, and you even can use external GPUs. So before the M1 came out, I had actually external GPUs, and I would train with external GPUs as well, where I would plug in eGPU into it. And basically the framework looks like this. So you have the Create ML framework. You can give it images, text, columnar data, click a button, and then output it to Core ML. And in a nutshell, you can see it looks like this type of workflow. So first you download Xcode, you open it up, and then you right click right here, and you can see that it's in a hidden menu. It says Create ML. And this Create ML technology starts like this. First, you use the image classifier template, which we can see right here. And then you can go through and train an image classification model. Now, notice that there's a lot of different templates that you can choose from, including object detection, style transfer, classifications. I think there's some examples in the Apple documentation about people training, let's say, exercise applications. So imagine if you're a mobile developer and you wanted to build a fitness tracking app, right, where you are able to maybe training people to do maybe powerlifting or doing pull-ups or something like this. You could actually train it and then give someone access to take a picture of themselves or a video of themselves, and then it could tell you whether you're doing the exercise properly or not. So those are just examples of some of the things you could do. But what's great about this, and we're going to go through this example in a little bit, is that you can grab a small version, let's say, of the Kaggle data set, and you can just drop that onto the UI, and you can see here the way it works is that it automatically, if you structure your data the right way, where there's basically two folders, it'll automatically decide the classes, and then it'll automatically split the data, and then you can just click the button and train the model. And especially with smaller data sets, it'll train the model in, let's say, a second or 2 seconds, and then immediately you can start playing with it, prototyping it out. So from a rapid development standpoint, this really could be helpful in just determining the feasibility of a problem. And what's great about this as well is that almost everybody has a mobile device. And so you could use your mobile phone to create your own data sets. You don't even need to download a data set from somewhere else. You could take your iPhone, for example, and you could take a bunch of pictures of people or of things in a factory, collect the data, put it onto your computer, format it in that structure, drop it onto this thing, click the training model, and you have a full end-to-end prototype. So for me, this is a really good example of using technology to solve a problem for you, where you could do the same thing by writing a bunch of code and it could take you a month, or you could potentially in just a couple hours take all the pictures yourself, put them onto your laptop, use the software, click a button, train a model, and even put it directly onto your iPhone and have a prototype in a couple hours. So I think this is really the future of what's going to happen is we're going to be using these high-level tools to very quickly solve problems. And again, you can see here's the example of this model here and how it works. A couple of things I'll start off with is that I'm going to maybe move this tool over here. So see this, if you go to Xcode and you right click on Xcode, if you have a Mac, you would select the options, I'm sorry, not the options menu, you would open up Xcode first. And then once Xcode is launched, you then right click on it and go to developer tools right here, open developer tools. And one of them is Create ML. So we'll go ahead and select this, and then we'll create a new document. And then here's when you do new document, it's basically the project definition. So it'll let you pick what kind of machine learning model you want to do. And in particular, I'm going to stay with this one, which is image classification. And then we can call this cats, dogs, ML. And then I'll just put this onto my desktop. And then what's neat about this is that really we're pretty much ready to go. And I can just drop some training data. Now, I had previously taken some data from a Kaggle project and just cleaned it up a little bit. Let me just show you what that looks like. It looks like this, that I have some images for cats, right? I just took 100 just to make it a little bit smaller. And then similarly for the dogs, you can see these are all the dog photos here, like this. And really all I have to do, as long as it's in that structure where we can actually throw this away. Basically, as long as there's whatever you're trying to classify is in a directory and there's an equal number of images, then you can just drop it right on top of this. So we go here and we just drop it. Let me just get rid of this. Drop it right on top of this like that. Notice it automatically figures it out, right? There's 2 classes, 200 items. It automatically figures out how to do validation. And then one of the other things that's kind of cool that you can do is you can enhance the accuracy of your model by adding, noise, blur, crop, all these kind of data augmentation features, which again, if you're doing this yourself with machine learning tools, could really take a lot of time. But I can rapidly prototype this thing, and then I just select this, train, there we go, processed 200 images. And even with all those really complex things that I did, notice that it comes up with a very good validation, 96.8%. If I go to evaluation here, we can see this. Here's the training, here's the validation. So basically the validation shows us that there's a small amount of overfitting here. And then if I want to test it out, now all I need to do is just find some other image. So I can basically put this to the right here like this. Yep. And then I can maybe just pull up another web browser and just find some images of cats and dogs. So let's go to cat image, and here we go. That looks like a good one. So let me see if I can open, link a new tab, and let's find this, save image as, and we'll put this onto, we'll say kitten, put that into my desktop. And then if we go back here, we can just click plus or drag it, find that kitten, there we go. And there we go, we see 100% confidence. Now let's find some kind of a dog image. Here we go. Let's take this, save this dog. Okay, I think, yeah, I can just do this. And unless, I guess for this one, I can just click on this image. There we go. And you can see as well, there we go, 100% confidence. So pretty easy as well to just prototype, and test the feedback loop, right? Just literally seconds to do this. And then the other thing that's neat about this is that notice that the output shows us the ability to look at the metadata, right? So it says we could actually give it some descriptive information here. I think we could have put this, I think if I do this, or I say like, this is cats and dogs, I could add more metadata to the project. Let's try that. And if I go back to my model, I think I might have needed to do that at the beginning, but basically I can add all this information in here. I also can look at the inputs. So like, what is the image format? And then also what is the return value? And then basically in terms of getting the model, I can also just either select open model in Xcode or even download it. So if I say save, I can take this machine learning model and just give it to somebody else. And here we go. Here's my Core ML model. I also can open it up in Xcode. And what's neat about the Xcode utility is that it actually gives you the ability to start prototyping stuff very quickly. So if someone else, let's say, gave you this, you could start to prototype it and play around with that whole feedback loop. So really, I think the CreateML framework, CoreML framework and CreateML tools are really a very powerful way to rapidly prototype computer vision models without needing to write any code. I mean, that's really, it in a nutshell. So let's kind of shift gears here for a second and go back to this, and I'll show you a little bit more of what you can do. So this is basically what we did. You saw that even with doing a lot of data augmentation, it happens in just a few seconds. And part of it, again, is because Apple owns the hardware and the software and the framework, they can make it all work really well together, where even in the case of Google Cloud, if I was trained that, I think it could take maybe 10 minutes, but it takes a second to train this model on my system because of how tight that integration is. Another thing to be aware of as well is that you also can convert it to a different format. Like Onyx, I think, is one of the ones that we're seeing a lot that is pretty interesting. And let me just make this a little bit bigger here. So Onyx is an open neural network exchange. And so this is an open standard for machine learning interoperability. And there's actually a bunch of examples of people using, let's see, there's a picture here of getting started, and you can see that cloud services, pre-trained models, exporting. There's examples of people taking Core ML. Like, here we go. Here's all the conversions that you can do with the Onyx format. Is like there's a lot of these different ones, and here's Core ML right here. And so here's an example that someone has. They say import Core ML tools. You just give it the location for the model. You then load it, convert it to the Onyx format, and then you could deploy it in Azure, right? Or you could deploy it with some other cloud platform or Kubernetes or something like this. But the core idea here is that you can export it into a more unified format very easily, but you could first prototype and build the tool with on your laptop. And I think that's a very powerful workflow to be aware of. So one of the other things that you can do as well, and there's a notebook that you can take a look at, is you can install the CoreML tools inside of Python. And then if I wanted to, I could even convert it. I could even download a model from, let's say, TensorFlow, and that somebody at Google had trained. And then, so we showed how you could convert it to Onyx, but also I could take a pre-trained model from somebody else and then convert it to CoreML. And you can see here, this is the walkthrough of the code. I download this model right here. I think this is like the labels of where the model lives right here. And then I go through and I convert this. Once I convert it, this is this code right here, CT convert. Then I update the metadata right here. And then finally, it will create this machine learning model, right? If I right click it and I download it, and in fact, I think let's go ahead and do this. Let's try this out. So if I click on this notebook here, hopefully this still works. Let's go ahead and try this out. I click on this model, Apple's CoreML tool. Let's go ahead and do pip install. We'll run this. This installs a CoreML tool. Okay. Next up, we'll import it. There we go. And now we will download the model. And so what this will do is download the this particular Keras model. There we can see this is where it is right here. And then we can load the class labels for the model right here. There we go. And now we can say import KaizenML tools, and then we can actually convert it. So this is where that conversion step would take place. There we go. All right, and now what we can do is we can add some metadata to the model right here. Add this metadata, and then now we just say model.save, and we save it as a KaizenML format, right? So again, Google created this, but I converted it into KaizenML. There we go. And now look, it's now sitting here. So if I go to this this directory right here, see how it's right here? I can go to this and download it. And now once I download it, what I can do is just make this a little bit smaller, like this, and then I'm going to take that model, which should be, let me just find it on my computer real quick here. Let's go to downloads. Here we go. So here's the model that I downloaded. I put it right here. And notice that now Apple recognizes that it's a format that it can use. So I just double click on it. And look, there we go. Now it opens up this model, and I've got this class labels. We can see there's 998 class labels. And then we also can look at the layer distribution here, all the different aspects of how the machine learning model was created. And then if I click on preview, we can actually go through here and test it out, right? So that's what's pretty cool, is that I can leverage all of this computational training and resources from somebody else, but get to prototype it with a really intuitive tool like Apple's technology. Now, what do I want to test it with? Let's see what it can do. Oh, there we go, great white shark. That would be a good one. So let's go ahead and find a great white shark here. So great white shark image. Let's go ahead and grab this. Here we go. This looks like a good one, and we'll save this on our desktop, and we'll call this shark. And now that I've got this model here, I can just click this plus icon, find that shark, and then there we go. It says 66% confidence. This is a great white shark, and even thinks it's possible it's a low confidence, but it might be a tiger shark, or it might be a hammerhead shark as well. So basically, I can start to prototype this, improve it, maybe use transfer learning. But I think that this feedback loop of being able to download and convert things from somebody else's pre-trained model is pretty awesome, and a great way to leverage multiple different technologies to rapidly test out a computer vision scenario. So we went through all that, we downloaded it. Now the other one that I wanted to bring up was Google's AutoML and edge-based computer vision framework. And in particular, one of the things that we see is that a lot of these will use this hardware solutions. And the reason why people are using it is the same reason why the Apple M1 technology works so well with my computer and how I can do predictions, is that there's chips that are very efficient at doing predictions. So this has the TPU technology associated with it, and this is the Intel Movidius. So they have their own neural networks built onto the chips, and they allow you to, let's say, train a model using a cloud platform, and then export it so that it works on this particular platform. And so what we'll see is that Google and Apple in particular have this vertically integrated stacks. And that's why they're able to have such a good workflow. And so in particular with computer vision, there's 4 things to be aware of. You can write the models yourself from scratch. That's, people have been doing this for a long time. You can also use AutoML vision, or you could download a model like what I just did, or you can use an API. So let's really briefly look at what a Google AutoML Vision walkthrough would look like. So if we go down here, if you wanted to do this from the terminal, you would add a policy, you would maybe copy the data from the shell into the Google Cloud Storage, and then what you would do is you would get something that looks like this, right, where you're able to visually inspect the image, and then you just go through here and you select train the model and evaluate, and you would select, let's say, AutoML here, and then when you're done, what you'll see is that it will give you these evaluation tools that will show you how well the model performs. So it's very similar to Apple's CreateML process. And then when you're done, the other thing to be aware of is that it gives you the ability to export it. If you wanted to, you could export it as the CoreML package, and it would work very well with your iOS device. Or what you could do is you could actually download it and use it with an Android, JavaScript, etc. So let's take a look really quick at what that looks like on their platform. So if I go to the console here and I look at their AutoML system, let's go through here, AutoML. Here's an example of something I'd done a little bit ago, and so this is a data set that I uploaded, and you can see that one of the neat things about uploading the data into their cloud platform is I could start to filter the data, explore it, maybe visually inspect it. Like, for example, roses, if I go through here, maybe I want to look through and make sure that everything is good data and there's not a problem. Like, for example, this is not a rose, right? There's a problem. This would be maybe something I'd want to delete before I retrain the model, because it's going to make it a less accurate model. Once I've got all this, I also would then go to train. Notice that it shows every different iteration that I've trained. And this one, I trained one for an online model. So this would be a cloud-based model. This one I trained for mobile model. And it shows me that this one took 32 hours to train. This one only took half an hour to train. And we see the actual accuracy as well. So let's take a look at this one real quick. If we say see full evaluation, what it'll also do here is give me the confusion matrix. Let me look at the different predicted labels, and we can see the false positives. For example, that roses sometimes were confused with tulips, right here, and then also I could scroll this a little bit and see, if I wanted to do a prediction, I could create a model that had different levels of a confidence threshold for like an online prediction. And then finally, if we go to test and use here, that you can deploy the model online. You could just select this, or this is the part where you could export it to other formats. You could just download it as TF Lite, and we just saw the example, right, of how I converted a TF Lite model to the CoreML. Or you could download it as JavaScript, which is an interesting way to deploy your computer vision model. You could also download it directly as CoreML. You could put into a container. Let's say you were going to deploy it to Kubernetes. This would be a good format. Or you could go to the Coral Edge devices, which are the hardware, like the specific TPU. Now let's go ahead and take a look at this real quick. If we look at the Coral technology, that one of the things that you can see here is that all of these hardware solutions, here we go, they're really very helpful for prototyping in particular, or for making production devices. I think for the best one I would recommend for prototyping is, at least from a cost and a capability standpoint, is this USB accelerator. And you could take the model that you trained from Google Cloud and put that model directly onto this device, or even take a pre-trained model. That's another example. You could take a pre-trained model, put it onto this device, And then once you've got it onto the device, because it has the TPU chip, it will do the prediction on there. So you don't even need to have, let's say, a GPU that's an NVIDIA GPU on your Windows laptop, for example. You could just use this and it would do the prediction directly on the device. So that's one of the nice things about this workflow here, is that it can go to so many different locations. And in a nutshell, you also have the metadata that allows you to inspect, again, what's happening with your data set and, all that kind of stuff. So there's a lot of advantages to using a cloud-based platform because of all the different places that it can go to. So that's the Google workflow, but they're not the only one that has a cloud AutoML solution. Another example would be Microsoft Azure. And there's a couple different ways to do Microsoft Azure's AutoML. One of them is the console. So, for example, you could basically programmatically access the AutoML SDK, and you can basically do that by using Python, or you can use the console. And the console, you would say create new here, and that's one way to do it. Or you could just select AutoML. And if we look at this example here, here's one where I decided I wanted to create a new data set, and I would just upload whatever data set I wanted to into the Microsoft Azure Machine Learning Console. Once you've done that, then very similar to these other solutions that I just mentioned, you would select the task type, so classification, and even you could select this if you wanted to have it use, let's say, a GPU cluster. So you would have to provision that GPU cluster first, but once you've provisioned it, you could say select deep learning, and then at this point, it would go through and train the model. And one of the neat things that we're starting to see more and more of here is that the AutoML frameworks will have explanations built into them. And so this is really, I think, one of the other advantages to using platform tools is that this would take a lot of time to build all this technology. And instead, you can leverage the platform. It'll give you important information about why it came up with the prediction that it did. And another aspect of this, as I mentioned earlier, is that once you maybe have the feedback loop working, where you understand how the whole model works, you could then go to the programmatic access of the model. So you could go through and call the Python API and maybe do 10, 100, 1,000 different iterations of different models that you want to try and different configurations you want to try. And so now you're working at a higher level, where a typical data scientist, they could maybe do one training per month. But if you're using a high level framework, maybe you could train 1,000 models per month, because you're programmatically telling all these experiments to run, and then you're observing the outcome of these experiments. So that's Azure. There also is AutoML. And so one of the things to be aware of is that they have a solution called Autopilot from AWS. And there's a bunch of different examples of how it works. But in a nutshell, you take your data, maybe it's tabular data or computer vision data, and you then select what you want to predict. The model is automatically created, as well as tuning the hyperparameters. You then have the ability to look at what's happening with the model and then select the best model yourself. So this is really what a data scientist would do, except for the fact that a machine is doing it better. And now if we go down here and we look at the autopilot experiment with SageMaker, and you say new autopilot experiment, what you would do is then put your data into the S3 location, so the data lake. Once you put that data into the data lake, you would then go through and create an experiment. And in particular, here's an example where we have an autopilot experiment. And notice that I say that the data is in this S3 bucket, and I even give it the specific name for the data that I'm training with. Once I've done this, I scroll down and I say submit, and it submits the model, and it goes through and starts to run a bunch of different experiments. Once it's done, then once it's training, you can actually click on the resources tab, and it will show you all of the different instances that are running. So, let's say you had a giant cluster of machines, you would see how much, how many of these machines were actually being utilized for this particular model, and maybe tune it a little bit or choose different types of machines that you want to run based on the budget that you have for this experiment. And then finally, you would go through here, and this would get you into the output of what actually occurred. So again, thinking about a traditional data scientist that maybe doesn't believe in cloud computing and thinks that cloud computing is bad, or whatever religious reason they have for not liking cloud computing, they're going to be taking maybe a month to do something that a machine can do probably 1,000 times quicker. And in particular, here we go, it went through and it tried a bunch of different iterations of algorithms, of different hyperparameters, and notice that it shows me a breakdown of the different accuracy levels. And now maybe I want to select the one that has the best accuracy. It even told me automatically. All I do is I go down here and I select that model and I right click on it, and then it says deploy model, and I could put that into a production environment. So for me, I've definitely heard many, I think it's a lot of times professors in particular that seem to be very, against these automated tools. I don't know why, other than maybe they've never had a job in the real world. So I've worked in the real world, so I'm very for automation. But I don't know why you would be against automation, but why would you do something worse and slower that a machine will do automatically for you? So I think this is one of the big takeaways, is that these automation tools are definitely going to be a part of most data science and machine learning, and the people that embrace them are going to be much more productive than someone who only does everything themselves manually. And again, this I think is a great example of that. Now, those are commercial tools, and you can make the argument that the commercial tools potentially are costing a lot of money, and so are there ways to do it without costing a lot of money? And there are actually a bunch of open source AutoML tools as well. And in particular, one of the open source AutoML tools that seems to really have a lot of traction is a tool called Ludwig. And it was actually developed by someone who worked at Uber. And in particular, the way this works is that here's a kind of walkthrough, you could pip install it, and then download some data. And then really, look, this is all you need to do is just say, I want to do an experiment, and you give it your data set and you give it your configuration file. So for me, this is really helpful, and a great workflow where, again, if I wanted to do some machine learning and I want to really, really quickly get something done, why wouldn't you just write a script where you had a bunch of different experiments you wanted to do? You kick this off, go to sleep, wake up in the morning, and you see all of the different results of all the different models that you train. And it's free, right? Because it's open source AutoML technology. And then you take a look at it, and then you see the different models that you could experiment with and later put into production. The other thing that's very interesting about Ludwig is that you can see the version right now is that or the older version, I guess, was they have support for pandas, which I think a lot of people have done, the support for this framework called Fast API for doing predictions. But then they started to add things like support for Dask, which allows you to do work with bigger data sets, but use Pandas API, and also Kubernetes. So there's support for Kubernetes. So I think we're going to see a lot of traction here as well, where people are embracing the higher level tools to do work so that you're much more productive. I guess it's like using a bicycle versus walking. You certainly can walk for 20 miles, but it's a lot easier to ride a bicycle. Same thing with Ludwig. I think for many experiments, tools like these are a very good choice. Another one to be aware of is this FLAML, the fast and lightweight AutoML. And this is one that came out of Microsoft research. And if we see this example here, we can see, basically only 3 lines of code. You can say from FLAML import AutoML, and then you would say AutoML.fit. Here we go, X-train, Y-train, classification, and then that's it. You can train a model. So here's a more comprehensive example here where I would say, pip install, go through here, load the iris data set, right, which you probably experimented with, go through here and do AutoML, go ahead and set, what your configuration should be. Maybe I want to do 10 seconds. I want to have my metric be accuracy, and then I want to do classification. You then go through and you fit this model. You then do a prediction, and then finally you export the best model. So again, I think this is the workflow of the future, is that you use high-level tools, at least initially, at the very least, to initially figure out the feasibility of problems automatically versus doing it all yourself. And here we go. Here's the output. You can see it went through. It figured out the best model, and it shows you that it selected the XGB classifier, and then it even shows all the different things like the learning rate it picked, all the different hyperparameters as well. Again, why would you do this yourself if you could have a machine do it for you? At least the initial phase. Doesn't mean you're limited to this. You could always tweak those hyperparameters later manually, but it gives you a good starting point, or in many cases, the final solution. So there's other open source AutoML frameworks as well to be aware of, like H2O AutoML, AutoSKLearn, Teapot, PyCaret, AutoKeras. These are all different examples of AutoML frameworks. And I guess, in a nutshell, really the takeaway here is that my opinion is that for computer vision in particular, and for MLOps, that you should embrace these high-level tools because they allow you to figure out the feasibility very, very quickly of a problem, and also what is the best approach. And it doesn't exclude you from using things manually. It's actually more inclusive because you know what the right thing is to work on. Now let me kind of go back here again to kind of look at this other example way back here. So I guess the big takeaway that I'll bring up here is that I think the biggest misconception about, let's go to, the biggest misconception about this AutoML technology, or even cloud computing technology, is that I think many people get really caught up in the word data science, and it's like a, people make it very too precious, essentially, like, oh, data science, or they get very emotional about AutoML. It's like, oh, AutoML, it's taking my job, it's replacing it. But if you look at it from a systems perspective, again, if you look at, let's say, a Tesla, for example, this has so little to do with what's really happening, right? Because you need to automate the features. You need to figure out, how to build a system that can decide what features are important for the problem. You need to have your software system automated so that you're not introducing bugs that are software bugs. You also need to automatically be able to deploy not just the software, but the model itself into the car, right? It's possible you may need to deploy a change like every day, right? So if you don't have this capability, you could be the best data scientist in the world, but you can't deploy your changes. You're not going to have a system that can use that machine learning. Likewise, and this is again why it's confusing to me why people are against some form of cloud computing is now academically, if you're writing research papers, maybe you don't care about cloud elasticity because that has nothing to do. But in the real world, you have to find the capabilities for compute and storage. And that's what cloud computing does. It allows you to kind of scale things up and down. And then if we go to the accuracy detection here, like data drift, this is another one where if you're constantly getting new data, you're going to need to have some kind of capability that can detect that there's differences. So a 10% change, a 20% change, a 40% change of the data, do some alert that says the model needs to be retrained and then potentially redeployed into, let's say, the Tesla vehicle or some car. Likewise, if you can't reliably get the data and put it into a location automatically, you can't even do data science, right? So this is a precursor to even doing data science. Is, does the data live inside of a location where I can analyze it, and does it have the capacity to scale up and down automatically? And that's where the automation or data operations aspect occurs. So in a nutshell, I think this is probably one of the most important things to be aware of with cloud computing, with AutoML, and with computer vision, is that you have to think about things from a systems methodology, and that AutoML, data science, they're very, very tiny part of the problem. It doesn't mean that they're not important, but they're one of many things that are important. And one of the best ways to never get something completed is to only focus on this, or only focus on this, or only focus on one part of it. But this is the goal. The goal is, does the model go to production? So again, going to the Tesla, either the self-driving is better today, or it's worse, or it's the same. Which one is it, right? Every day. Is it better, or is it worse, or is it the same? What technique you used in data science or what hyperparameter you have is irrelevant. It's is your self-driving better? Is it better? Same as if you have the same methodology for, let's say, cancer detection, or for something in the health industry. Are you better at detecting cancer? Are you the same, or are you worse? And really what techniques you use and all these other things ultimately are not as important as, are you saving people's lives? Are you improving outcomes? Same, again, if we go to the vaccines, right? There may be new vaccines that needed to be created for COVID-19 or for other future, outbreaks of things. Either people are getting better, they're the same, or they're worse, right? This is the way you evaluate whether your approach is successful. And I think it's not talked about enough. And so my recommendation would be, for projects that you create, you think about it from an outcome perspective, not from a technique perspective. Is my outcome improving as a result of what I'm doing?